Hello, everybody. In this video, we're going to continue our discussion about the sun, and we're going to dig down and start looking at how do we know what we know about the sun. We're going to look at some of the fundamental things that govern the sun, this concept of hydrostatic equilibrium, and then we're going to use that along with some pretty amazing observations that are out there to build a model of stars. The model of stars that we use is called the standard solar model because we built it and we can test it versus the sun. So we're going to get deep down and actually look underneath the surface of the sun to start building our knowledge of how stars work. All right, sounds like a weighty task. I'm pretty excited about this one. Hang on one second. I got to make sure I can share my audio, share computer sound, and we can get started with looking at the concepts of the standard solar model and all sorts of things to adjust this time. The standard solar model and helioseismology, how we actually determine the interior structure of the sun. But before we start that, we have to start with one of the primary concepts that controls the size of a star. It puts a star in balance. It puts the sun in balance. So if we think about this, the sun sitting out there in outer space is this enormous ball of plasma and gas, a spherical ball of plasma and gas with a mass of 1.99 times 10 to the 30th kilograms. That is a heck of a lot of mass, which means that the sun generates a lot of gravity. It has an incredibly strong gravitational force associated with that much mass. And what does gravity do? It tries to pull everything together. So if left alone, if nothing else were happening, the sun would, just being a ball of gas, would keep getting smaller and smaller and smaller and smaller and smaller and smaller and smaller as gravity squeezes everything together. There must be something, since the sun is always pretty much the same size, it's a pretty stable object. There must be something that's preventing gravity from just crushing it. What is providing the force that can fight off the internal crush of gravity? Well, gravity is pulling everything inwards, and the sun is generating a whole lot of energy through nuclear fusion in its core, which is going to create a very, very high temperature and a lot of pressure that pushes back outward. So the interior of the sun is hot, creating a thermal pressure pushing outward. Plus, there's a lot of thermal pressure, or a lot of pressure associated with the nuclear reactions in the core of the sun. So we have essentially gravity trying to pull the sun so it shrinks and gets smaller and smaller and smaller. And then we have thermal pressure that's trying to blow it up like a balloon. So we have these two different forces at play: gravity pulling inward and pressure pushing outward. And if we put these two things in balance, if we make the strength of that gravity trying to pull everything in equal the pressure trying to push everything out, then those two will balance out and the star will be stable. We call this balance between outward push of thermal pressure and the inward pull of gravity hydrostatic equilibrium. I know it's a mouthful of a term, but it is a principle concept for understanding the stars. The sun is in hydrostatic equilibrium. Gravity trying to pull it in is perfectly balanced by the internal pressures, thermal pressure trying to push it outwards. And this hydrostatic equilibrium, where this balance point is reached, actually determines the size of the star. The physics of all this will tell you how big a star will be by how strong gravity is pulling in and how hard pressure is pushing out. One of the things that falls out of that is the size of the star, the size of the sun. Okay, hydrostatic equilibrium, something that's going to be said from here pretty much all the way to the end of the semester. So make sure you get that concept. And part of the consequence is you have the nuclear fusion happening in its core. You're trying to move that energy to the surface of the sun. There's all sorts of internal things that are happening inside the sun, a subject for another video. But we have all of this stuff happening in the inside of the sun that's creating this outward pressure. And then we have the gravity that's pulling things inward, which creates a lot of internal movement in the sun. In fact, it creates all of these waves in the sun, these types of very similar to sound waves, that it creates all these vibrations as everything is moving around in the sun. It creates all of these vibrations in the sun. And we could say that the sun is essentially ringing like a bell, all of these internal vibrations. And what we're seeing here is actually a video of the vibrating surface of the sun. So, all of these internal forces are causing the sun to ring like a bell. And what's really, really, really cool is that we can actually detect these vibrations. We can look at them here from Earth and see them. As all of these forces push around, they'll settle into what we call these standing waves. Kind of like if you pluck a guitar string or pluck a violin string, it'll just vibrate up and down. That would be a standing wave. I'll show you an example of this on the next slide. But the entire sun sets up into these 3D spherically symmetric standing waves, which are solvable by mathematics. But you can think about it also as the sun is ringing like a bell with all of these different waves traveling through it. And we can actually take those waves, this sort of vibrations of the sun right here. If we could translate those into the human audible range, we could talk about the sound of the sun. So let's go ahead and hear what the sun sounds like. So there you're hearing these vibrations of the suns, all of these different frequencies overlaying on top of one another to give this sound that the sun is constantly producing. Of course, you can't like put your ear out into outer space and hear it. Sound, you need something for sound waves to travel through. But this is what the sun would sound like if we could turn the frequencies into the audible range. We are doing a audio simulation of all of these vibrations in the sun. So the sun is ringing like a bell. These waves that are traveling through it, these standing waves, create these oscillations, these vibrations in the sun. And we can study these vibrations to actually determine the interior structure of the sun. This is what it would look like. These are what the vibrations would look like, where blue would be a point that's popping up and red would be a point that's moving down. So they'd just be oscillating up and down and up and down and up and down. We can study all the different frequencies. So studying these solar vibrations is a field of study called helioseismology. And with it, just like we can use seismology, the study of seismic waves generated by earthquakes on Earth to determine the interior structure of the Earth, we can use these sound waves traveling through the sun to study the interior of the sun in a field called helioseismology. So what is helioseismology? It is the science, it is the process of determining the interior structure of the sun by studying all of these vibrational oscillations, the sound of the sun, the ringing of the sun like a bell. So all the energy being produced, moving around in the sun, creates all of these sound waves, these seismic waves. And you can see the different, this is just showing different modes of the waves. This is the L equals 200 mode, the L equals 60 mode. You don't need to know any of those advanced concepts. But you can see there are all sorts of different standing waves that get generated in the sun. This is what a standing wave would look like. Doesn't look like it's traveling. You just have an oscillation up and down between these nodes. So if we were looking at the sun, there would be parts of it colored blue that would be popping up out of the sun, up, out. So you have the parts that are coming up and out, and the parts that are going down and in, and those would just be oscillating back and forth, these ringing like a bell waves. And we can detect those here on Earth because if there's material that's popping up, moving towards the Earth, all the wavelengths will be slightly blue shifted. And there is material that's going down, popping away from the Earth, it'll all be red shifted. So we can look at the surface of the sun, use the Doppler effect to actually start seeing all of these different oscillations in the sun. And you have already probably gotten the concept that this is really, really, really complicated stuff. But the basics are pretty easy. The energy moving around in the sun, it's causing the sun to ring like a bell, causing it to have all these internal vibrations, of which we actually heard an auditory simulation of it. And we can study those oscillations to actually look at the interior structure of the sun, because what those oscillations are, what the wavelengths are, things like that, are determined, how it travels through the sun is determined by the interior density structure of the sun. So we can use helioseismology to actually probe the interior structure of the sun. These vibrations will actually give us the internal structure of the sun, which is just absolutely phenomenal. Okay, so now we can take all of those observations and let's set those aside over here. We can look at the helioseismology to calculate the interior structure of the sun. We can observe the surface temperature of the sun. We can observe the composition of the sun. We can observe the size of the sun. So we can observe all these amazing properties of the sun. But we can also model those. We can go ahead and build a model of the sun where we're going to throw in all the physics with a full mathematical treatment, go to all the fundamental concepts of physics, all the principles of physics, put that into our model of the sun to build a model sun, a fake star, a model star in a computer. And what kind of physics are we going to throw at this? Notice this is all in green text. You by no means need to memorize all the things, the standard solar model, the standard model of the sun. You don't have to know the physics that goes into it, but it includes things like hydrostatic equilibrium. You should know what hydrostatic equilibrium is. It includes things that are called equations of state. An example of an equation of state would be the ideal gas law for gases. It includes energy production via nuclear fusion reactions in the core. It includes the energy transport, how energy is transported through each layer of the sun. It includes the chemical composition of the sun and how that changes over time. So you can put all of this knowledge into a computer model and build a model sun. So now we have a model sun, and we have all these amazing observations of the sun from its composition down to its interior structure via helioseismology. And we can compare the two to see if the physics that we're putting in can model the sun. Do we understand how a star works? Do we understand it well enough to reproduce a model of it with a high level of accuracy? So when we build this model of the sun with all the physics, we call that the standard solar model. And the things that go into it are all of these physics, and the things that you can get out is you could get out what its density, that's what's here on the y-axis, as a function of distance away from the sun. So you know the density structure of the sun, compare that to helioseismology results. You can get the temperature structure of the sun from the core all the way up to the surface, as well as a host of other properties, because now you have a complete model, computer model of the sun. So what's amazing is we can build this model of the sun, the standard solar model, and it'll predict things like the radius of the sun from the hydrostatic equilibrium part, the luminosity of the sun from the nuclear fusion reactions in its core, its composition, the internal density structure. So this right here, we can produce that from the model. And then we can compare that to everything that we observe about the sun. So we can take our theoretical model of the sun, compare it to our observations of the sun, and ask, how good of a job did we do? And the standard solar model is a amazingly accurate model. It can reproduce pretty much every one of those data sets with 0.1% accuracy. So within 0.1% of the observed values. That is an astounding level of success, that we can put the physics into a computer and produce a model of the sun that matches observations with 0.1% accuracy. Holy cow. Which means that we can trust the numbers that the model puts out for the things that we can't observe and get really, really fine, detailed things like the core temperature of the sun. And it's based on the success of the solar model that gives us confidence that we understand how stars work, our host star, where we have a whole bunch of observables to test it against, and we are constantly getting more observations to test it against and refining our model to be better and better and better. And since it's so amazingly accurate, we use this as the standard for all the stars in the universe, to build models of all the stars in the universe, which then we can use this to see how stars change over time, how they evolve, how they age, how they live, how they die, all hinge on building this successful standard solar model here and comparing it with the observations we have of the sun. Of course, when we extend this to the stars themselves, we'll use the observables of stars to check those models against. But here we see the core for how we understand stars. Absolutely astounding, just starting from a little bit of physics, that we can get to this point where we can understand all of these properties of the sun and predict them with an incredible amount of accuracy. So, that is our study of the sun, or the beginning of the study of our sun. We still have a long way to go, and I will see you in all of those videos where we continue to talk about the sun as a star.